Les Frost, Technical Architect at Capgemini. I celebrated my 20 years with Capgemini a few weeks ago, so I've been here quite a while. I'm going to talk to you about facial recognition and image recognition, because I think you need to understand more about it, because it's really interesting technology. So let's start with this straw poll. Who thinks that image recognition and facial recognition are important for business? Not many? You? Okay. How many people think it's... Oh, how many people understand it? Do you know how it works? One? Good. Okay, so after this, you should be able to go away and talk about how it works. Right. Let's start with the... So I'm going to go through... Why is it important? Why is this stuff suddenly become really important? Why are people talking about it all the time? I'm going to talk about how we teach computers to recognize images. So that's going to require at least 5 minutes of concentration, but it's not too difficult. Bear with me. I'm going to talk about deep learning and neural networks, and I can already feel it go, ooh, I don't know about that. But we're going to go through them. Yeah. I'm going to talk about why suddenly this sort of stuff's become affordable and practical. I'm going to touch on some of the business applications of it, and then I'm going to talk to you about how developers today can use this technology, and I'm going to touch on what we've been doing downstairs in our hackathon. So by the end, you're going to know a lot about facial and image recognition. Right, let's start with why is this stuff important to business? So this story is a really good one. So Facebook did a report last year which basically looked at the pictures that you upload and worked out whether you were a dog lover or a cat lover. And you think, why is that important? Well, that's important because you guys, like me, are putting up more and more pictorial information that describes what you do. Yeah, so I'm a cyclist, yeah? I put up pictures of me on a Cannondale bike, and marketeers go, hey, that's nice. I'd really like to know that information. So this is quite interesting. You know, the pet food industry is worth £24 billion, and Facebook can, without you saying anything, work out whether you've got a cat or a dog, or quite a lot of other things, actually. So why is it important to business? The answer is you tell people an awful lot of stuff by uploading images. A picture paints 1,000 words, and that's entirely true. Right, so let's talk about how that might work. Right? So you look at that, what do you see?
Disconcerting.
Yeah, absolutely. Yeah, absolutely. So your eyes and your mind and your brain are really fantastic at that. You instantly look at that and you go, yeah, that's a person, it's a man, it actually looks like that guy is presenting a bit. Right. What does a computer see? Absolutely. So that's a dump of that JPEG file, right? It's just bits and bytes, right? So how on earth does a computer go from a file like that, bits and bytes, to any sort of understanding what's in it? Your brain's really good at it. How does a computer do that? You want to know? No? Okay, let's go through that. Right, so it uses, so there are techniques, deep learning, machine learning, neural networks. Let's just pick out those terminologies. So machine learning is the idea that you've got a generic algorithm, and what you do is you feed different data into it. And as a result of feeding different data into it, you get different logic. You don't change the code, you change the data. Right? So, for example, I'll talk you through a convolutional neural network soon, and I know you'll worry about that term, but it's not that difficult. It's a classification mechanism. You feed in data into it. The same algorithm can be used to classify numbers. So if you wanted to recognize handwritten numerals, same algorithm as can be used for recognizing dogs, cats, whatever. What you've done is you feed different data into it, but fundamentally it's the same algorithm. So that's machine learning. Algorithm stays same, data you feed into it differs. Deep learning is the idea that those algorithms are based on these things called neural networks, which I'll explain. And a convolutional neural network is a type of neural network that's really good at understanding positional data, like images. and I can sort of feel, you go, "Ooh, convolutional neural network, that's really complicated." Well, we'll get to the bottom of that soon. So that's the terminology. So what we're going to do now is go through how a convolutional neural network works. I can sort of sense those terminologies. It's hard, isn't it? Right, so this is, if you're in this field, there is a guy called Brandon Rower who's written lots of information about how a neural network works. So what we're going to do is we're going to talk through a neural network, and its job is, if we feed in an image of an X or an image of an O, it's going to tell us what that is. It's a basic classification. Obviously, normally I might do this on lots of different things, and it would be more complex, but this will take you through the basic idea. Now, it's not quite as easy as that, is it? Because X's can be translated or scaled or rotated or thicker, thinner. But we still want this thing to tell us whether it's an X or no. So deciding is hard for a computer. Yeah? Computers are really literal. Yeah? They look at this problem and go, is that the same as that? Well, actually, when you sort of look at the differences, it's actually not that easy to get to. So literally, that isn't really equal to that. So how do we break that down? How do we move away from this sort of literal comparison to something a bit more intelligent? Right. So the first thing that convolutional neural networks do is they match parts of an image. Right? So they break the image down into parts, and they match parts. That's the first thing they do. So in this particular case, we have an X there, we have an X there that's slightly rotated, but we can still see parts within that image. So this is a technique that allows them to progress. The basic idea is that you have features within your image. So in our case, for an X, we have a diagonal white line left to right, a cross in the middle, and a diagonal white line right to left. Yeah? That's what our X is made up of. And what we do is we apply those filters to that X. Yeah? Really easy, isn't it? So we look for matching parts. Yeah? And particularly we use this technique called filtering. So now I'm going to mention the maths word. So you might want to hang on a bit. But effectively, if we represent our X, as values, bits, ones for the white, negative ones for black in this particular case, then what we can do is we can do some arithmetic. What we can do is line up that feature with the image. We can work out bit by bit whether that image matches the thing we're looking at, and then we can add up that value, and we can do some mathematics. So let's look at that. It sounds complicated, but it's not. So we apply that filter in this position, and basically we work through matching. Yeah, so it matches. That matches that. That matches that. So in this case, we get an exact match. Yeah, so that filter matches that part of the image exactly. So what we do is we sum up that. So it adds to 9. We divide it by the number of pixels in this filter, and we get perfect match, 1. And we store that. And then we move it. So if we try that diagonal in the middle position there, we get a slightly different value. There's a partial match now. So some of the pixels match, some of them don't. So now we add those up, divided by 9, we get a weighting of 0.55. So we get a partial match. Yeah, makes sense? So what we can do is effectively we can filter this image. We can apply that filter in every position and get a map. And you can sort of see it, can't you? You can see it matches here, it matches there, it doesn't match there, it sort of matches in the middle. Yeah? That's very cool. That's what convolution is. Yeah? So when you hear those complicated terms, convolutional neural network, convolution just means apply it in every single position. Right? So it's not that complicated, is it? So we do that. So the second technique that convolutional neural, what we then do is we can apply this filter and we get a map, and we can apply every filter. So if in this case we've got 3 filters, we apply it to our X and we get a different map, effectively. And that map tells us how well that filter matches that. Got that?
Why are the second ones different?
Sorry, say that again.
That's the same. You've got different filters.
Yeah, we're feeding in an X, and we're applying the filter that is for the middle of the X, the filter that's for the diagonal and the other diagonal. Yeah. So one image, we can apply multiple filters, and we basically get this idea of a filtered image. And they're just weighted. They're just maps of how well that image fits that part of the picture. Now we do something called pooling. And again, what we do is we pick a window. In this case, I've picked a 2 pixel by 2 pixel window, and I move this window across this image, picking the maximum value. This is called maximum pooling. And so I visit that, the maximum value is 1, I go here, the maximum value is 0.33, and I go through the whole image. And I get, effectively, a smaller image which still tells me where things match. Now, what that does, if you think about it, it takes into account variability. So I'm looking in a part of the image, and I'm taking the maximum value. So if the diagonal matched slightly miss-center, I would still match it. So those trickier cases where I've got things that are translated or extended or fatter, now this max pooling idea says, well, I might not have got an exact match there, but I might have got a match there. So by taking a maximum value, you're sort of doing fuzzy matching now a little bit. Still with me? Good. Only one more step. So we have this idea of pooling. So we take an image, we pool it, and we get another map, which tells us how well that thing maps. So a stack of images again, we feed it through this pooling idea, and we get different maps based on our different filters. Then we do something called normalization. There's a lot of mathematics behind this, but basically it is the idea that you now run through this map, and every negative value you change to 0. There is a very good, if you ever want to read it, it's a very deep paper about how this works, but fundamentally, the next stage of our neural network goes through our image, and it gets rid of negative values. And that's called rectified linear units, grand name for quite a simple process. And again, we can take a set of maps, we can apply this transformation and get a new set of maps. And that's how neural networks work. They have layers of processing that do that sort of thing. So convolution, try a portion of a filter in every position on the map. Pooling, step through the map, choosing maximum values, and linear units, get rid of negative numbers. And when people talk about deep learning, that's what they mean. They mean that you can have many of these layers of mathematical processes. Because what's interesting about this is, if you like, the input into one of these layers produces another map which can feed into subsequent layers. So they're all just numbers in a matrix, effectively. So the layers can therefore be repeated. So you can do some convolution, some regular linear units, more convolution, and that's what's meant by deep learning. They are effectively mathematical processes applied to an image, repeated over and over again, and that's where the deep bit comes from. Right. At the end of the day, this thing is trying to decide whether we put an X or an O in it. And so when we get to a point, we need to use this data, this sort of strong matching data, to vote for an X. So these numbers get turned into probabilities, effectively, and those probabilities determine what this convolutional network is going to derive in terms of its value. Is it an X or is it an O? And so some values, as you go through the network, vote for an O, and some values vote for an X, based on how well those filters fit the image. Still with me? Sort of? Okay. And so what happens is that those probabilities effectively result in combined probabilities. So in a particular case, it might be the case that when you feed an X into this neural network, if it's a very wobbly X, you end up, the neural network will say, I think that's an X to 92%, or I think it's an O to 51%. And these are all probabilities that sort of derive the conclusion of the neural network. That voting idea is called fully connected layers, and it's just a way of deriving a value at the end of all that processing. And that, again, they can be combined. And so what happens is you get a neural network that takes an image, it applies the filters, it does some pooling, it does some voting based on probabilities and gives you an answer. It says, that thing you fed in, I'm 92% confident that's an X, or I'm 51% confident it's no. So you might be sitting there thinking, well, how do those numbers get derived? That's a bit, I don't really get it. So the answer is, the neural network does something called backpropagation, big word. But the idea is that if you fed an X, a definite X, through this machine, you should get an answer. And you can calculate an error. If you put something in and you know it's an X, then you can do a calculation that says, I put in an X, my neural network has said it's 92% sure it's an X. Well, actually, then it's got an error, hasn't it? It's slightly out. And if I put in an O, it's slightly out as well. So what I can do is I can have this idea that there's an error in my neural network. And so what I'm going to do is carry on manipulating those values and changing them to drive down the error to its minimum value. And that's what teaching a neural network means. Feed data through it, keep evaluating those probabilities until you will get to a point where the error is minimum. This is a screen print from the hackathon downstairs. They're using an open source framework to do neural networks. And you can sort of, it's very technical, but here it's saying, I'm on my 4th iteration, I am looking through your data, and I am 95% sure. And you can see these probabilities go up and down as the neural network takes on more and more photos. In this case, they've got 10,000 photos of cows, 30,000 photos of non-cows, and their job is to feed in a photo and for this thing to say it's a cow or not. And it works really well. When you get to things like zebras, it gets a little bit confused. It says, sure about that, might be a cow. So these things are not precise, but they are fairly good. So we've listened to that about the theory of neural networks. What does a designer of a neural network actually get to choose? Because it sounds like it's all fixed. So what the designer of a neural network gets to choose is, how many features am I going to look at when I do that convolution? How many layers am I going to have in my network? What's the order of layers? And most of the research in neural networks at the moment is about combining layers. The techniques, the algorithms were written in the 1950s and 60s. What the people are doing now is, how can I order all those techniques to get the best recognition of the particular thing that I am looking at? So in terms of facial recognition, what happens is you get these convolutional layers, and the first layer sort of detects light and dark, the next layer detects edges, the next layer sort of groups those edges into shapes, bits of ears, bits of noses, and the next layer pulls those shapes into faces. That's basically how it works, using those techniques that we just described. So if those things were written in the 1950s, why is suddenly everyone talking about them? The answer is games. Seems to be the answer to most things. So games processing has produced graphical processing units that are capable of doing hundreds of billions of calculations a second, which is exactly what you need to do facial recognition. Data. The other thing you need is photos, and we are projected to store 1.2 trillion photos in 2017, right? So we've got algorithms that have been around for years, we've suddenly got massive processing power, and we've got massive amounts of data. So suddenly we've got sort of perfect storm for facial and image recognition. If you get some quite interesting ones, so you get data sets. This is a data set that you can test your neural network on for facial expressions. Right? So if you're building a neural network, you can go to a place, get an MMI data set, and it sort of says, yeah, that's disgust, and that's fear, and that's... So you can train your neural network on a set of photos that says, here's 1,000 photos of somebody who's angry. Here's 1,000 photos of somebody who's happy. And effectively, those neural networks will look through the images and work out what the differences are and be able to classify, look at a photo, is this person happy? Interesting. Right, applications. Well, obviously, now it's mainstream. It's gone on Apple iPhone, so it's mainstream as far as I'm concerned. I'm not a great Apple fan myself, but hey, it's mainstream. Those of you, I mean, I'm from a medical family, and the medical industry take millions of photos. They take photos of CAT scans, MRI scans. There are classification systems today that, you know, this one's taken 130,000 pictures of skin disease, and it is able to detect malignant or benign skin cancer more accurately than a trained dermatologist, right? Because it's all about matching and looking at patterns in images. And computers are really good at it, far better than we are in these particular cases. This is quite an interesting example. Take hundreds of photos of diseased leaves, scan your tea plant with your phone, and it'll tell you what's wrong with your tea plant. Yeah? ASOS, fashion envy, quite like the suit that he's wearing, photograph, find matching images. Yeah? Good. Yeah?
Does that happen a lot?
For you, Ben, I must admit, it's this envy. So this is quite an interesting one. This is quite an interesting one. We've all seen those horrible stories about lorry drivers ploughing into the back of parked cars because they're not paying attention. So facial recognition and image recognition can tell you whether someone is paying attention, on their phone, texting, all those sort of things. These are all now possible using image recognition. This is my favourite. This is the one I am mostly interested in. This is the idea. I take a photo of a car park and I work out whether there are any cars in the spaces. This is the one for me. So when I drive up, it texts me saying, you know, row 4, space 7 is yours. Yes. Brilliant. So if you go in any facial image recognition competitions at the moment, this is the one that is most people are trying to solve at the moment. Yeah. Well, I don't know about that. Obviously, you'll have heard of you know, driverless vehicles. They are all based on the idea of image analysis, of frames of video, and steering round stuff. Yeah. So again, this technology is applicable in that whole area. So if you're a developer today, how do you get into this stuff? Well, most of the big vendors have pre-built facial recognition services. So in the hackathon downstairs, we've been using the Amazon recognition system. This is a pre-taught neural network. You can upload your photos. It will tell you whether you're an old a person, a dog. It will detect images. It will do all that sort of stuff. If you want to build your own, you can use something like TensorFlow, which is open source, which again they're using downstairs in the hackathon. Open source framework for building your own neural network. Just load in your own data. There are lots of data sets, and there are lots of people who are prepared to give you massive amounts of graphical processing units on the cloud to do these massive calculations that you need to teach your neural network really quickly. The hackathon downstairs has been looking at sort of 3 aspects. Facial recognition, so take your photo and your name, later on turn up, they'll take your photo, they'll tell you who you are. Image recognition, so they are teaching a TensorFlow neural network about cows, non-cows, it could be anything you wanted. And there are also another group looking at these more advanced applications of image recognition. I'm hoping they've made some progress on this parking spaces, because that's the one for me. So I suppose my message is image recognition in its sort of widest sense is very important to business. It's a marketeer's dream. The amount of information you can get out of a photo is massive. But I would also say it's becoming mainstream technology. You know, this is technology that your average developer can now go and put in applications. It's applicable, it's available to people. There's open source software, there are cloud services that everybody can use. The cost of entry is really low. You don't need to pay for any of this stuff. You can use this technology. And the rate of innovation, I mean, just stepping through some of those business applications, you can instantly start thinking about, you know, how this technology can be applied. The rate of innovation, given that that cost of entry has gone down, will just continue. It's rapid and it will continue. And I suppose my message to you is it's a good time for you to understand how this stuff works and think about whether you could use it in the business that you're in. And that's me done. Questions? How complicated did you find convolutional neural networks? All right?
It is going to be, I think it's very, very good, very interesting. There you look talking about human faces or animals, and so you can do broken pipes, broken passages, all those.
Yeah, the AIE downstairs have a good demo. If you want to build an extension and you look at your house and you go, what brick is this? And they've got the demo that says, look at the brick, a phone, they've got a brick classifier, so they fed brick photos into a neural network, and it can say, to get a nice matching brick, you need to go to being tuned by that one. But they're the sorts of things that is absolutely fantastic, because they are all about understanding what's in an image. Perfect.
How fast is it? Is it near real time? If you have have you seen that doorbell that's got like an internet camera in it? So
yeah,
you can see who's passing. Could you actually just go to your house and it'll let you in, like the Apple phone will let you in?
Yeah, so if you look at a lot of TED Talks nowadays, there was a guy recently who walked out into the audience with his phone, on his phone, recognising people. Yeah, they're in real time. So they've really, there's been lots of research into the optimising the processing of neural networks. They can be really quick. They're now getting, I mean, to steer, obviously, but it's pretty quick now. Facial recognition, they've got that down to
Can it
in this second of Microsoft.
There's a plant walk that we've been doing in our garden. You
Yeah.
take a leaf off a plant that likes at somebody else's garden.
Yeah.
Shove it onto your phone.
Yeah.
And the software will say what plant it is.
Yeah, absolutely.
That's
You
quick
used
like
to
that.
but it was the people at Capgemini.
There is one like that. This is actually a leaf. You can take it off and put it onto your phone. It will tell you what the plant is. I've got it on my iPad actually.
Yeah.
The other
Definitely
life
makes
is still it groups your photographs based on cats.
Yeah.
Does it automatically.
Absolutely. Yeah. So this technology is mainstream. It's going to be very large, and it's just your imagination that limits it. Really, it's applicable to many types of problems.
It's not often we're kind of ahead of the curve or up with the trend in public sector, but we've got them working with the AIA at the minute, looking at whether we can take a driving theory test, so people can do it from home using facial recognition, whether anyone else is coming into shot.
Yeah.
And that's looking quite interesting.
Can you go further to start looking at you and saying, oh, well, you're this type of person, so start interpreting what you look like into, are you likely to shop, are you likely to behave in a certain way, are you likely to commit a crime?
I haven't
HR red card.
I haven't
Will you
seen.
work hard?
I haven't seen.
He'll do emotions.
Yeah,
The iPhone X will do the whole image and then create your emotion.
It can certainly use your contextual photos to do that sort of stuff. Here's Les he likes that sort of bike, but whether it can do that in your face, I don't know.
But it's worth looking into, because then it removes all the need for all the custom data. That's actually why bother. I can just tell by looking at you whether you get shot.
The thing from my perspective, it's so interesting, I get it, but it's
It's really dangerous. This is exceptionally dangerous. I thought your point about, I was posting it actually, your point about posting all your images on Facebook, about the products you do, the people you see, the people you're with, the clothes you wear, it's so intrusive.
I suppose Dave Stokes downstairs who's doing the demo used to work at Devon's, and they were thinking of putting RFID tags in your clothes. So that when you walked into a store and said, you are wearing that sort of shirt and that, the next shirt and so and so, we've got some offers for you. And Boots were looking at it as well, but they steered it away from it because they thought it was too intrusive to their customers, and that was like 10, 12 years ago.
What's intriguing for me is if you look at GDPR, right, which is all about personal data, and we always think about data health and you on about your address and all of this. That data Facebook's using, I mean, I can see a point where that will be stopped even doing that, because effectively I'm not giving permission for them to do that, even though I have to ask them.
Exactly. You can have a heart attack. There won't give you any insurance.
So I'm not, I agree with you. I think they may well become a tipping point where this stuff becomes intrusive. Sorry?
It's not just Facebook. You've got Google.
Yeah, everyone's doing it.
What Lily just said there, if you map something like Fitbit data, it would still have a heart attack. I mean, it's going to
I will be able to tell that.
it is crazy the phenomenal amount of different things we look at together, and they're going to know us better than we know ourselves.
Okay, now insurance. Your insurance premiums will be sky high.
Because I'm always drunk.
Hey, I'm discovering quite a lot about this stuff.
So I think
Good.
that's good.
So hopefully that was helpful, and you can go away
That's exactly
knowing more.